Hello, I'm James Monroe, and I'll be talking about passive athermalization in this video. Now, passive athermalization is an interesting problem, especially for infrared optic materials. And that's because if you have an infrared optic lens material, you'll have a change in focal length that is negative. So as the temperature increases, you want your sensor to get closer to the lenses. Well, this is a fairly common design that's used to passively compensate for that natural shrinking with increasing temperature. And what you do is you select an outer housing material that has a low coefficient of thermal expansion, so it expands a little bit with increasing temperature, and a high expansion material inside that expands a lot with increasing temperature. And so you can get your focal length to shrink with increasing temperature. Now, the trade-off is that this housing is much bigger than the focal length. And you have to increase the length of that housing by the dimension of this inner tube or inner material. And that length we call L2, and this outer length we call L1. Now, I'm really interested in understanding how the thermal expansion coefficient of this first material and the thermal expansion coefficient of this second material influence the length of this inside part. Because you can only make this housing as small as your focal length. You can't get any smaller. And so we're going to be talking about how to develop a figure of merit that will enable us to compare different lens materials selected for this inner housing and outer housing. So when taking a look at the figure of merit or trying to develop one, what made the most sense to me was comparing the additional length of the housing to the smallest length of the housing possible. And in a system like this, the smallest length L1 can be is equal to the focal length. And the additional length required above the focal length is equal to L2. So we need to develop an equation or a system that tells us how the material choice for material 1, or the outer housing, and material 2 will influence this figure of merit. So if we start to think about a uniform temperature change, that the outer housing is going to want to expand. And we can define that by the change in length of this L1. And the inner housing is going to want to expand as well for a normal material. And that's going to be delta L2. And so the change in this air gap, which would be characterized by the change in focal length, is equal to the change in length of the outer housing minus the change in length of this inner housing. And with this setup, of course, the right hand, or going to the right, is going to be positive. So what we're saying is the thermal expansion of this focal length, as it gets bigger, is going to be equal to this expansion minus this expansion. And if we take a look at the linear coefficient of thermal expansion for a material, as well as the simplest version of the change in focal length, or the required change in air gap here with changing temperature, we have two very simple equations. So the change in length due to a change in temperature is the thermal expansion coefficient times the original length of that material times the change in temperature. And the change in focal length again, for a single thin lens element, is equal to delta, which is the coefficient of thermal defocus, times the focal length times delta t. So these are very simplistic equations, but they get the point across, and they're of the same form. A material property times a length times a change in temperature. So we can plug these two equations into this larger equation, and we get something that looks like this, with alpha 1 L1 delta t minus alpha 2 L2 delta t. And we'll notice that the change in temperatures, or the change in temperature, can be canceled. And that tells us, because of the linearity of the equation, it doesn't matter how big the temperature change is, you're going to see the same result. So this simplifies a little bit to alpha 1 L1 minus alpha 2 L2. Now we have an equation that's in the form of lengths and material properties. And our figure of merit is, we want it to only be dependent on L2 and F, this length and this length. And we still have this L1. Well, we can take that L1 out because we can notice that L1, the length of L1 is always going to be equal to the sum of the focal length and L2. So we can substitute F plus L2 in for L1. We get delta F is equal to alpha 1 times F plus L2 minus alpha 2 L2. And we distribute the alpha 1. Delta F is equal to alpha 1 F plus alpha 1 L2 minus alpha 2 L2. Now we want to get common terms together, so we bring the alpha 1 F over. We get delta F minus alpha 1 F is equal to alpha 1 L2 minus alpha 2 L2. Combine common terms. F times delta minus alpha 1 is equal to L2 times alpha 1 minus alpha 2. And then we can divide both sides by F and divide both sides by alpha 1 minus alpha 2. L2 divided by F is equal to delta minus alpha 1 divided by alpha 1 minus alpha 2. And now we have this figure of merit that is in material property terms. So it's only dependent on the material selected for the lens, the material selected for the outer housing, and the material selected for the inner housing.